In programming, we often see the same issues come up again and again over time. Design patterns are solutions to these commonly occurring problems that have emerged and evolved over time. The following is a high-level overview of over 150 of the most common ones. It is by no means an exhaustive list. It's also not necessary for you to use or even memorize all of them. They're simply tools, and this video is intended to raise your awareness of what's out there, serving as a springboard for further learning. Feel free to use the timestamps in the description to jump to the ones you need, or check the links in the description for additional resources. Creational patterns. These patterns help with dynamically creating objects at runtime. The Singleton pattern. Used when you only want one of something. Singletons ensure there's only one instance of a class at any given time, and that it can be accessed from anywhere. It starts by defining a static instance and a way to assign it, often in a constructor, an initializer method, or via lazy initialization. The instance can be made into a property with a public getter and a private setter, and an optional backing field. If duplicates are possible, you might destroy the extra ones, or use a flag to ensure persistence. You can also use generics to make a base singleton class, and leverage inheritance to hide much of the boilerplate code. Overuse of singletons can lead to tight coupling, making it difficult to scale and test code as scripts become too dependent on them. The factory pattern. Factories help you create objects, similar to a constructor. It starts by designing a static method, usually named create. The object is instantiated, and some logic might be applied to it before returning the created object. Different subclasses might have different logic applied at the time of instantiation, which can be hidden behind the factory method. Parameters can also be passed through to help determine the specific implementation of what should be created. Factories are often made for a broad base class or interface, such as spells, enemies, items, abilities, etc. The core idea is to centralize creation logic, reducing direct dependencies, and keeping your code flexible. Abstract factory. A more generic version of the factory pattern that has an interface or abstract class as its base. Specific factories are then derived from it. Abstract factories are often used for groups of related objects that go together and which share common attributes or styles. In this case, a create method is generated for each object within that family. The concrete factories then override the base method and apply specific implementation to all members. For instance, a UI might have buttons, drop-downs, and checkboxes. One factory produces Windows versions of each, while another produces Mac versions of each. Abstract factories are good for organization and scalability, but require more setup initially. The builder pattern. Used to create complex objects step by step. Its main purpose is to avoid having too many constructors, or constructors with lots of unused parameters. It does this by separating the construction of a complex object from its final product, allowing the same process to create different variations. Begin by defining an object you wish to build with a bunch of placeholder properties. Define a builder class with a constructor for that object, and provide methods to configure specific properties, like name, size, color, etc. Often, these are done as set functions. Once all the details are in place, call a method to build and return the final object. This forces construction of the object through the builder. Fluent Builder, or Fluent Interface. A more flexible form of the builder pattern that adds method chaining. Start with a standard builder, then make each configuration method return the builder itself. This lets you construct objects more intuitively, with methods such as with_name, with_health, with_weapon, etc., all in a single line. It's a great way to make your code more readable, especially for objects with many properties, where you want the option to only use some of them, without necessarily using all of them. The order in which the object is built also does not matter, as each method is only working on a single property. The prototype pattern. Not to be confused with the prototyping phase of production, which comes between planning and testing. Prototypes focus on creating new objects by cloning existing ones. Start by defining a method in your base class that performs the cloning. Depending on your language, this might be as simple as calling a built-in method, or you might need to copy properties manually. Prototypes are ideal when creating an object from scratch is expensive or complex. An example of when you might use this would be in Character Equipment screen, wherein you have a placeholder mannequin as your visual. Rather than spawn a new character in each time, You spawn the character in once and simply copy over its clothing, weapons, and outfit from the inventory to the dummy. Unity Engine employs the prototype pattern when generating prefabs. The original object is stored as an asset, while copies are spawned in the hierarchy as clones. Prototypes are fast and efficient, but be mindful not to override your original reference unintentionally. Object pooling. Creating and destroying objects can be computationally expensive. Pooling reuses objects instead of creating new ones every time. Start by creating a pool. Usually a list or queue works best. Fill it with a number of objects to start. When an object is needed, take one from the pool. When it's no longer in use, return it to the pool for reuse. If the demand exceeds what's available in the pool, then and only then create more. Visual objects can be hidden from view until called from the pool. Additional logic might be necessary to reset variables like position and rotation, either when calling or returning, to ensure predictable behavior. This pattern is especially helpful for objects that are frequently created and destroyed, like bullets in a shooter game. Testing is often required to strike a proper balance for how many objects should be created initially. Too many can be a waste of memory, as objects go unused, while too few defeats the gains of having a shared pool. Managing the pool carefully is key to avoiding memory leaks or performance issues. Pools can also make use of generics to hide boilerplate code. Lazy initialization. Certain objects might not be required for the entire life cycle of an application. Their creation could be expensive, or their mere existence could lead to problems if not done in a particular order or at a particular time. In such cases, we delay the object's creation and setup until it's actually needed. A guard clause can be used as a stopgap the first time we try to access the object. We check if the object is null or otherwise has some default value. If it is, we create a new instance and return that. Otherwise, we return the current value or instance. Some downsides of lazy initialization include increased complexity, more difficult debugging, and hidden performance issues, as the point in time of creation is not always obvious. The Multiton pattern. Where singletons only allow one instance of a class, multitons allow several, each identified by a unique key such as a name, number, or hash ID. For a small number of instances, you can declare multiple static instances. For example, a single-player game might have a static instance of the player class, whereas a local co-op game might have static instances for player 1 and player 2. For larger or unknown amounts, multitons can be stored in a static dictionary. When a new instance is needed, check the dictionary. If the key already exists, return the existing instance. Otherwise, create and store a new one. Multitons are great for things like configurations or databases where you need multiple distinct singletons. Just keep track of your keys to avoid unexpected results. The Object Mother pattern. A fancy name for a factory that creates placeholder objects with pre-configured or default settings for use in rapid prototyping or presentation, but which might not necessarily wind up in production. The object mother can be useful when the focus is not on the creation of specific objects or data itself, but when object creation is needed to generate large amounts of examples to test some other aspect of the program. For instance, an inventory system might have hundreds of items, all with their own stat values and behaviors that need balancing, but we don't yet have that data, so we create a factory that produces a variety of placeholder items in order to test other aspects of the system that don't necessarily care about what specific items pass through them. They just need something in order to work, such as drag and drop, trading, or persistence. This pattern can be helpful in verifying whether the values and behaviors you get back in testing are the ones you expected. One downside of the object mother is that it can be misleading if your tests require very specific data in order to pass. Structural patterns. These patterns help in composing and organizing classes or objects. Marker interface. Names and tags are a common way of identifying objects, but strings are often prone to typos, particularly if you have to use them more than once. Similarly, it can be hard to keep track of ID numbers or hash values and know exactly what they refer to. Instead, a marker is a class or interface attached to an object and is used solely or primarily for identification. It can start off as empty and later evolve to have additional logic in it. By using a type instead of a string or number, most IDEs should alert you if there's an issue. Markers can be turned into components or derived from using inheritance. They are a great way of filtering your searches when you need a particular type of object, especially if you name them well. The adapter pattern. If you've ever tried to plug a 3-pronged device into a 2-pronged outlet, you know you need an adapter. Similarly, this pattern acts as an intermediary, translating one interface into another that your system understands. For example, in game development, you might need to integrate an external library with your game engine. The library might have a different API than your system expects, so you create an adapter class to bridge the gap. Begin by defining the target interface your system uses, then implement an adapter class that translates requests into calls that the external library understands. While this pattern ensures compatibility, it can often add overhead if overused. The bridge pattern. If a class has 2 or more dimensions along which it can inherit, the bridge pattern attempts to split these and rely on composition instead, such that one becomes dominant and simply references the other. For instance, objects might be classified by shape or by color. An object that can't inherit from both groups will need to pick one to be the base functionality, in this case shape, and that class will then have a reference to the other. In this case, all shapes have colors, but not all colors necessarily have shapes. Usually, this is best resolved by considering that inheritance describes what a thing is, whereas composition describes what a thing has. While the bridge pattern is quite flexible, it's best reserved for larger projects. The wrapper pattern. A wrapper is a way to enhance an object's behavior without altering its underlying code. Child classes can often serve as wrappers by implementing both the base functionality and additional behaviors as well. Alternatively, we can make a new class or method that performs all of our desired logic plus something else. This can be especially useful if, for some reason, you don't have access to modify the original class or method, or if modifying it would break other parts of your code that depend on its current implementation. For instance, we might have a log system that writes messages to the console. Supposing we want to add timestamps and other data about a particular log. Instead of rewriting the original logger class, we create a wrapper class with a method that adds timestamps to the original message before writing that to the console. While useful for minor changes, excessive wrapping can obscure the original logic. The decorator pattern. A form of wrapper laid over top of an existing object. Decorators are designed to compound their effects, dynamically adding or removing layers of complexity. Picture a game where a character can gain temporary buffs like speed or strength. Instead of hard-coding every combination of buffs, you wrap the character in decorators that modify its behavior on the fly. Start with a base interface, create concrete classes for each behavior, and stack them as needed. This pattern is highly flexible, but can lead to confusing code if too many layers stack up. The facade pattern. Complex systems can often have too many moving parts for a user to manage. The facade pattern is a wrapper that simplifies things by creating a single entry point. For example, when building a save system for a game, you might have separate classes for writing files, compression, and encryption. Instead of calling them all individually, you build a facade class that handles the whole process with a single save method. While it makes the system more user-friendly, the downside is that it can hide too much detail, leading to less control. Facades can also run the risk of violating the single responsibility principle if tasked with doing too much. Extension object pattern. Extensions allow a class or type to be modified even after it's been compiled, meaning we no longer have access to change the underlying base code. Both adapters and extensions can be used on software that's already been developed. Where adapters allow us to link to existing features, extensions let us create brand new ones. For instance, extension methods are static methods belonging to a type or class that allow us to tack on additional functionality. A type like int or string cannot be modified, but their behavior can be extended, such as int.add1 or string.sort characters alphabetically. The flyweight pattern. Memory usage can balloon when you have many similar objects, like thousands of enemies on the battlefield. The flyweight pattern reduces this by sharing common state across objects. For instance, instead of storing redundant data like enemy types and textures for every enemy, you keep one shared copy and link each enemy to it. Begin by separating intrinsic or shared properties from extrinsic or unique ones. Then, create a factory to manage the shared state. This pattern excels in efficiency, but adds complexity in managing the shared resources. The proxy pattern. Sometimes you need a stand-in for another object to control access, improve performance, or add functionality. For example, in a multiplayer game, you could use a proxy to represent computer-controlled opponents or players not currently loaded into memory. The proxy provides placeholders for data and loads the actual object when needed. Start with an interface that the proxy and real object both implement. The proxy then forwards calls to the real object as needed. This can save resources, but introduces a slight performance hit when changing over. The dynamic proxy pattern. A specialized variation of the proxy pattern, where the proxy object is created dynamically at runtime, often using reflection or similar mechanisms. It allows you to intercept and control interactions with an object without modifying its code. For each real object, no explicit proxy class is written, but a single generic proxy mechanism can handle multiple objects or interfaces. For example, let's say that you have a service class. You create a logging proxy that takes the service as input, logs when a method is called, and then forwards the call. This pattern is great for auditing, security checks, or caching, but it can make debugging harder since you're working through layers of abstraction. The module pattern. Groups related variables, methods, and other logic into a single cohesive unit called a module that encapsulates functionality. It provides a way to organize code into reusable, maintainable, and self-contained modules. Modules typically expose only the methods and properties needed by the outside world, keeping their internal details private. Once a module is defined, it can be difficult to change as other systems come to depend on it. Modules can also risk becoming interdependent on other modules. Behavioral patterns. These patterns help govern the interaction between objects. The observer pattern defines a one-to-many dependency where, when one object changes state, all its dependents are notified. The two most common examples of this are delegates and events, though custom ones can also be created. The easiest way to think of an observer is, something happened, and now these are all the things I want to have happen whenever that action occurs. We start by defining the observer and decide on an appropriate time to either call it, if it's a method, or update its current state. A subject will have a list of dependents, often called listeners or subscribers. At some point, these get registered to the observer, usually when first created or enabled, and then later unregistered, usually when destroyed or disabled. When the observer is triggered, we loop through the list of all dependencies, if there are any, and notify them. More advanced uses of this pattern include event channels and event buses. Observers can be a powerful way to decouple code since the observer acts independent of whether anyone is listening or how many listeners it has. However, memory leaks can occur if subscribers are not properly deregistered. The strategy pattern allows you to define a family of algorithms, encapsulate each one, and make them interchangeable. This pattern lets you select an algorithm's behavior at runtime, promoting flexibility and adherence to the open-closed principle, meaning open for extension, closed for modification. Strategies often begin with an interface or abstract base class, with concrete versions extending from it. The base is used as a placeholder in other classes or methods until a specific implementation is defined. The strategy pattern is one of the most powerful and most commonly used programming patterns. It's often employed in things like spell systems, weapon systems, interact systems, and anywhere else in which it's desirable to swap out behaviors of a given type without knowing exactly what they are ahead of time.
I'll tell you, personally, I pretty much am a strategy pattern guy, right? I think the strategy pattern really is the basis of all patterns, right? I mean, it's pretty much, life is strategy. That's pretty much just use an interface.
The command pattern turns actions into objects by encapsulating them. We start by defining a class or interface, such as iCommand. Typically, this will have an execute method that gets called whenever a command is invoked. Commands can then be gathered together into a collection, such as a queue, where they can be processed in a particular order and at a particular time. Commands can be repeated by queuing up multiple instances, or they can be cancelled by removing them from the collection without invoking them. They can also be sorted and recorded to produce things like undo-redo or replay functionality. One drawback is memory allocation if too many commands are stored. The state pattern allows an object to change its behavior when its internal condition changes, effectively letting an object appear to change its class. This is particularly useful for objects that need to behave differently based on context, such as a game character transitioning between walking, running, or jumping. States don't just apply to characters, they can apply to anything that changes behavior in response to changing conditions, such as a chest, a dialogue tree, a quest, a UI element, or an entire game. The simplest form of this pattern is a Boolean flag, wherein an entity switches between two states based on some condition. More complex versions include if-else blocks, ternary chains, enums, switch statements, and finite state machines. The template method pattern defines the skeletal structure of an algorithm inside of a function, but defers specific implementation to subclasses. For instance, in a particular class, we define a method that calls step 1, then step 2, then step 3 in that order. However, each step is marked as abstract and must be overridden. In a concrete class, we might define each of these steps a certain way, and then in another concrete class, define each of them in a different way. We could even reorder the steps just by changing which one we define as step 1 and which one is step 2. The template method is sometimes used within the state pattern to define the various phases of a state, such as enter, tick, or exit. In Unity Engine, the mono-behavior lifecycle follows this pattern, wherein each phase occurs in sequence and can be overridden by a class that extends mono-behavior. One drawback of this pattern is that it's tightly coupled to the implementation defined in the base class. If we have unused steps, we can leave them empty, but we cannot insert new steps between existing ones, and must be mindful of the order of operations. Double dispatch. A process for choosing which method to call based on the runtime type of both the caller and the one being called upon, the latter of which appears as an argument in the method signature. Polymorphism is the principle by which a class can be treated as its own type or as its parent type, depending on context. For instance, all dogs are mammals, but not all mammals are dogs. Dog, in this case, extends mammal, and thus is polymorphic by virtue of inheritance. This can lead to behavior that varies dynamically and is somewhat unpredictable. Double dispatch ensures that behavior is chosen based on the type of both interacting objects, enabling flexible and dynamic operations without requiring prior knowledge of exact types. The visitor pattern. Separation of concerns means that a class should only be responsible for its own behavior and not have to worry about who or what it interacts with or when. The visitor pattern is a form of double dispatch that places the burden of responsibility on the visitor to determine what should be done during an interaction. This avoids creating an excess of references and is highly scalable as we can add functionality without modifying the underlying class. A visitor might have many different methods depending on the type of object it interacts with, but doesn't necessarily know which one to invoke due to polymorphism, and the fact that a class could be one of multiple different types at any given time. The class being visited is given the ability to accept a visitor and return its exact type at runtime, so that the visitor knows which function to invoke. The bottleneck in this pattern is with the visitor itself, as it will need to be modified for every new type of entity that can be visited. It's best used when many new functions need to be added to existing elements, but the set of elements itself remains largely unchanged. The Iterator pattern. A way to sequentially access elements in a collection without exposing the underlying representation. For loops and for each loops are a type of iterator. In C#, the IEnumerable and IEnumerator interfaces let you define and iterate over such a collection while applying custom behavior in the process. Chain of responsibility. An algorithm that passes a request along a series of handlers until one of them processes the request. Start by creating an interface or base abstract class from which all handlers extend. The interface stores a reference to its next handler and defines a method that assigns it, as well as an abstract method whose signature determines what kind of information it can process. Child classes then provide a specific implementation for how they should process data sent to them. If a class is unable to process the information, it passes it to the next handler in the chain. This continues until the data is finally processed or the chain runs out of handlers. One downside to this pattern is that it can make debugging more difficult as information is passed between many points of contact, like trying to talk to a real person on a customer service hotline. The Mediator pattern. A way to centralize communication between objects to reduce dependencies between them. Managers, registries, lookup tables, and repositories all tend to implement the Mediator pattern, as any class that needs information can simply call them directly and ask for data or methods stored there. Events and event channels can also serve as mediators by notifying all subscribers when a particular action has occurred. Mediators are highly scalable as they help enforce separation of concerns. The Memento pattern allows you to capture and externalize an object's internal state, preserving it so that you can restore the object to that state later. This is useful for undo and redo functionality in applications, as well as replays and version control. In gaming and emulation, it can be used to generate checkpoints and death warps, as well as save states to preserve persistent game data or prevent soft locking. This pattern can lead to excessive memory use if many states are stored. The Interpreter pattern. An interpreter's job is to provide translation between two languages, taking into account not just individual symbols, but also context. They can involve natural languages, programming languages, or both. If you've ever used a parser, such as int.parse or string.parse, you've encountered this pattern before, but it's possible to write your own. Indeed, the word parse means to analyze each symbol in a set and extract some useful value from it if possible. A dictionary can act as a lookup table for providing such translations. Depending on context, an interpreter can also perform some work on a value or set of values before returning a result. The Retry pattern. A means of executing an action and retrying it a specific number of times if it fails. This is useful for working with unreliable operations, such as network requests. We define a number of attempts and loop over our action until we either succeed in the action we're attempting or run out of tries. A try-catch statement can be useful if you need to throw an error or exception, alerting the user that the process has failed repeatedly. Property Change Listener. A specific form of the observer pattern where subscribers are only interested in listening for changes to a single property, rather than to any and all changes that might occur. Usually this occurs in a property setter or at the end of a function. When the value is changed, all dependencies are notified. For instance, the value of a slider might be stored as a property, and then certain things happen when the slider is moved, and its corresponding value is modified. Specialized behavioral patterns. These patterns have more narrow use cases in terms of coordinating object behavior. The Event Aggregator pattern consolidates event management into a single object to help decouple publishers and subscribers. Start by defining simple classes to represent events. Next, create a central hub to register, deregister, and publish events. The Event Aggregator is often made into a singleton. The aggregator holds a dictionary whose keys are our event types. Each type then maintains a list of subscribers. Various systems can then call the aggregator inside their methods and tell it to publish events as they happen. Other entities and systems can then call the aggregator to register as subscribers to those events, passing in their event arguments. Some downsides are that it can make tracing issues difficult and is prone to memory leaks if subscribers aren't cleaned up properly. The Null Object or no-op pattern. A default do-nothing implementation of an object to avoid getting null exceptions or creating excessive null checks. Some objects can't be used unless and until they're initialized, for instance lists. To get around this, we create the default implementation and assign it when an object is initialized. This pattern is not useful if you actually need the object to be capable of being null, however. The Black Hole pattern. A form of null object in which all methods and properties of a class also have default do-nothing implementation. The result is to swallow or mute all such methods and properties without side effects or outputs. One drawback to this pattern is that it has the potential to swallow genuine errors and unwanted behavior as well if used improperly, making it less useful if you need to trace such behavior. The Specification pattern. A way to encapsulate logic used for filtering and matching. Start by defining an interface for the type of object you wish to filter, and an abstract set of conditions to be met. Generics can be used for this purpose. Child classes will define a concrete implementation. For instance, a class that validates whether a person has reached a minimum age. We can then loop over a collection and filter out members that either meet or don't meet these particular requirements. The Role Object Pattern. An object that takes on multiple roles dynamically, independent of its type hierarchy, similar to the strategy pattern and the concept of character class in role-playing games. We define an interface or abstract class for the role with an execute method. Child classes will define specific implementations for what it means to act in this role. A target object then creates an instance of this role, which can be invoked or changed dynamically. Injection patterns. These patterns help reduce coupling by providing a code block with the things it needs to do its job exactly when it needs them. They are a key part of clean code, allowing classes and methods to stand on their own as they don't need to know about the existence of other entities outside of exactly what's provided to them. Dependency Injection. The act of providing a class or method with all of its required dependencies, rather than relying on external calls or global variables. Dependency injection is a core part of functional programming, but can also be used to great effect in object-oriented programming as well. Many software applications have an inspector as part of its user interface. Physically dragging assets and references directly into serialized fields can also serve as a form of dependency injection. Constructor Injection. In object-oriented programming, a constructor is a special method that creates an instance of an object. Constructors serve as an entry point to a class and can perform initialization logic on an object. They're usually named the same as the class they define. When building a class, it's often essential to provide everything it needs right from the start. Constructor injection does exactly that, passing dependencies as arguments, often assigning them to local variables and caching them for later use. This approach ensures that the class has everything it needs to function and avoids runtime surprises. A constructor method can be overloaded, meaning multiple versions can be created with different signatures that have the same name, but different parameters for different initialization schemes. Having many dependencies or creating many overload methods could become unmanageable for larger or more complex classes. Setter injection. Sometimes flexibility is key. With setter injection, you can give a class its dependencies after it's been created. Setter injection allows you to swap dependencies mid-operation or provide defaults, keeping the design open to change. You can directly assign a value to a property or pass in a dependency as the parameter of a method. In either case, some logic can be performed on the value before it's finalized. By delaying the assignment of a dependency, this can lead to uninitialized or null values that could lead to errors or other unintended behavior if not addressed. Interface injection. A way to define a setter function in an interface or abstract base class, forcing any class that implements the interface to also implement the set function. While less intuitive, this can guarantee a class has a means of setting its dependencies. This adds complexity, but can be useful if you plan on overriding the specific implementation of the setter in child classes. Architectural patterns. These patterns deal with the high-level structure of a project, organizing components in a way that makes your code easy to scale, adapt, and maintain. Clean architecture. An organization model that emphasizes the separation of concerns, with core logic being split into different layers and frameworks. This approach ensures a project is easy to maintain and test, but can feel over-engineered for smaller projects where you just want something that works with quick turnaround. In such cases, a brute force approach might be more appropriate. Layered or N-tier architecture. A way to divide a system into layers, each responsible for specific functionality, such as presentation, logic, and data access. This pattern is ideal for enforcing separation of concerns, but can lead to inefficiencies and tight coupling between layers if poorly designed. Model View Controller, or MVC. A fancy way of saying you should separate logic from visuals from input, and have these three systems talk to one another, rather than rely on direct dependencies on tight coupling. In the MVC pattern, data and logic are usually grouped together under model, though you might consider splitting those as well in larger projects. The Model View Model pattern. A variation of MVC in which an entity known as the view model one word, is responsible for mediating between the logic and the visuals. For instance, a player class might serve as the view model, coordinating player stats, the data, movement, the logic, and user inputs, the controller. The current state of the entity is then made public for other systems that need to know about it, such as an animator in charge of updating visuals. For smaller projects, this can feel over-engineered. Model View Presenter, a variation of MVC in which the entity in charge of handling visuals is given a more prominent role. For instance, a component in charge of playing animations or updating character sprites based on the model's current state. Alternatively, a presenter could be an entity in charge of updating UI, such as displaying player stats in a heads-up display. In either case, these should be separated from the logic, data, and inputs. Entity Controller Boundaries, or ECB. A design pattern focused on separating responsibilities into entities, called data, controllers, the logic, and boundaries, the interfaces. It's often used in applications where higher emphasis is placed on protecting data and creating a robust user interface. Otherwise, it's quite similar to the MVC and other patterns that promote separation of concerns. The pipeline or filter pattern. An approach that processes data through a sequence of steps known as filters, where each step transforms the data before returning it. Picture an assembly line where a part or product travels down a conveyor belt, having elements added, modified, or removed along the way. Complexity scales with the number of steps in the pipeline. Event-driven architecture, a form of organization that relies on the use of remote communication between components. Events, delegates, and observers are leveraged heavily. Highly decoupled and modular, it's useful for asynchronous systems. As with other event-driven systems, debugging can be difficult due to indirect communication. Event sourcing, a means of storing all changes to an application's state as a sequence of events rather than overriding the current state itself. The system's state is reconstructed by replaying these events. Useful when you need to keep a full audit trail of all changes to the system and require the ability to replay and reconstruct state, which is useful in event-driven systems. The downside is that this pattern can lead to large volumes of event data, requiring efficient storage and management. Rebuilding the state from events can be slow and resource-intensive, or complex to manage as the system evolves. The publish-subscribe pattern. As in, if you're learning something from this video, make sure you give it a like, share, and subscribe so you know when we publish new content. A messaging pattern where publishers send messages without knowing who subscribes to them, and subscribers react without knowing their publisher. A logging system is one example of this pattern. The input system in Unity Engine is another example, where inputs are treated as actions that fire whenever a button is pressed, regardless of whether or not any scripts are listening for said input. Microservices architecture. A service is a unit of functionality, or a component that performs a specific task. Services are generally self-contained and responsible for doing exactly one thing. Services are generally only called upon as they're needed. For instance, a service in charge of input handling, or a service that processes payments. The microservices pattern structures the project as a collection of small, independently deployable services. This pattern is highly scalable, highly modular, and can help isolate faults since each service is isolated and limited in its responsibilities. Complexity scales with the number of services, making it harder to manage communication between them. Service-oriented architecture. This approach structures applications as a collection of services that communicate through a common protocol, such as SOAP or REST. This pattern is useful for creating modularity and cross-platform communication, but adherence to rigid protocols can often make this pattern less flexible. It shares many of the same strengths and weaknesses as the microservice pattern. The Service Locator pattern. A way to centralize access to services by registering them in a global repository called a locator. This pattern is used when you need loose coupling between services and their consumers. By using generics and the Singleton pattern, we can effectively use the locator to call any service from anywhere, provided it's been registered. The trade-off is that this can be harder to debug due to hidden dependencies and encourage global state, making unit testing more difficult. The client-server pattern. Most people picture servers as large rows of hardware towers used in IT departments, but that's just physical equipment for storing and processing data. The client-server pattern merely splits an application into client components and server components, where a client is any entity requesting a service, and a server is any entity that provides it. This pattern is commonly used in web and mobile applications where service calls are made over the internet, though that's not strictly a requirement. A server can become bottlenecked if too many requests are sent at the same time, resulting in high load and reduced accuracy or performance. The broker pattern. A way to facilitate communication between distributed systems by introducing a broker component that processes requests and responses between clients and servers. Where a mediator actively manages the exchange, the broker merely points each party in the right direction, similar to a receptionist or dispatcher. This pattern decouples systems, making it easier to scale and manage. Blackboard architecture. An organizational structure used to solve complex problems that have no straightforward algorithmic solution. It relies on multiple components contributing incremental solutions to a central shared data structure called the Blackboard, which acts as a global repository for problem solving. A software inspector or node-based window can serve as a means of intuitively representing the Blackboard pattern, where the underlying collection or graph is itself the Blackboard. Hexagonal architecture, also known as the ports and adapters pattern. A port refers to an interface, while an adapter in this context refers to the specific implementation of that interface. In hexagonal architecture, the core application is surrounded by these ports and adapters, decoupling the core from external systems. It's ideal for systems that need to swap out external dependencies, like databases or input mechanisms, without affecting the core logic. Onion architecture. A form of layered architecture that organizes layers around a central core. It emphasizes separation of concerns, with dependencies pointing inward toward the core. The outer layers handle input-output, while the inner layers handle core logic and rules. For instance, characters in a video game might be represented as entities. Each entity has a reference to a core class. The core class is responsible for adding, removing, and fetching components. Components can include broad behaviors like movement, senses, collision, input, animation, etc. Each of these components, in turn, has its own domain-specific behaviors that get registered and sent back up the chain. We can then path to any part of the entity by entering from its core and going outward, or by one of the outermost layers and going back up to the core. This pattern requires a thorough understanding of dependency inversion, as it can get quite complex and is better suited for larger applications. Micro-Kernal architecture. This pattern provides a minimal core system that can be extended with plugins. The core handles only essential operations, while additional features are implemented as extensions. Common examples include operating systems, IDEs, and game engines, where external libraries and packages can be installed to extend base functionality. Care should be taken when managing plugins and to avoid bloating the core. Component patterns. Many object-oriented programming languages do not allow you to inherit from multiple sources. For this reason, composition is often preferred, which means we add behaviors to objects as they're needed, building them up like Legos. These patterns revolve around that concept. The composite pattern. A way of structuring code in which an object's data and logic are distributed across multiple components. It starts by defining an interface or base class, often called component, from which other classes will derive. Objects then maintain a list of all required components and can reference them as needed. Helper functions can be created to add, remove, or retrieve components, granting access to various properties and behaviors. One challenge of this pattern is ensuring uniqueness if an object has two or more of the same type of component without a means of distinguishing between them. The process of adding and removing components at runtime can also be computationally expensive. Component-based design. A paradigm where functionality is broken down into reusable modular components. Unity Engine relies heavily on the component pattern as a core design feature. All game objects maintain a list of components attached to them. The MonoBehavior class extends a class called Component, which allows developers to add or remove behaviors to and from objects, either directly through code or by manually dragging them in the inspector, which is often much more intuitive for non-coders. Entity Component System, or ECS. A component-driven design pattern that separates game entities into data, functionality, and systems that operate on them. Here, data are called entities, and functionality is stored in components. The organizational structure of this pattern can be more difficult to learn compared to other, more intuitive approaches. ECS is used for high-performance games or simulations that need scalability, like handling thousands of objects at the same time. Besides its normal component-based design, Unity Engine also has a built-in ECS solution, intended to work with its jobs on burst compiler packages. Component-oriented programming. A refined ECS-like pattern, where components focus more on encapsulating logic alongside data, rather than being purely data-oriented. It can extend ECS with more robust behaviors, used to create reusable, modular behavior on individual entities, or more straightforward entity management in simpler projects. This pattern can blur the lines between data and behavior, and lead to more complex dependencies over time. Data access patterns. Data access patterns deal with the organization of, access to, and interactions between data within a database. This is not just limited to something like Excel or Google Sheets, but can apply to any collection of data. The domain model pattern. A fancy way of saying we create objects that hold both data and behaviors. Domain refers to the subject or area the software is trying to solve, while model refers to the way solutions are represented and organized, usually reflective of its real-world counterpart. For instance, in the domain of online shopping, you might create items and have a cart object to hold those items. Items would then have data such as name, amount, or price, with methods to change name or apply a discount to the price. Cart will have items as its data and might have methods like add or remove. This pattern excels in complex domains and is often more intuitive, but demands significant upfront design effort and understanding. The repository pattern. An intermediary between logic and data, providing a clean, consistent interface for data access. It centralizes queries, making them reusable and reducing duplication. Think of it as a librarian who fetches the right book, the data in this case, based on your query, shielding you from the complexities of the library's organization. This pattern simplifies unit testing and ensures a clear separation of concerns. For simple projects, a repository might be overkill. A repository can also become bloated if not careful. The unit of work pattern. A way to manage transactional consistency by tracking changes to objects during an operation and ensuring all updates are committed as a single unit. Common actions like save, publish, or checkout are all forms of commitment that lock in changes made up to that point. By coordinating changes, it prevents inconsistencies and supports undo-like functionality. The data mapper pattern. A way to separate objects from a database by creating a way to match data between the two, rather than storing data directly within the objects themselves. This is useful if the data or the database source changes. This pattern increases the complexity of data access and requires greater care to maintain mapping logic. The active record pattern. Not to be confused with records, which are a data structure often used in functional programming. The active record pattern wraps domain logic and data access logic into a single class, where the object itself knows how to persist its data. This pattern violates the single responsibility principle and can become difficult to scale and test in larger systems. It's best used for smaller projects or where the object is directly tied to a row of the database. The query object pattern. A way to turn database queries into objects that can be reused and combined for flexibility and readability. This pattern is useful when you need to perform complex queries or when queries need to be dynamically composed. The downside is that it can create unnecessary boilerplate code for smaller queries or lead to an abundance of small classes being created. Table Data Gateway. A way of creating a class or interface for SQL operations related to an entire database. It serves as an access point for the data, but generally does not perform non-SQL behaviors on it. This pattern is useful for fine-grained control, tightly couples code to the particular database it's working on. Row Data Gateway. In this pattern, each row of a database represents an object, where each column is some property of that object. The object itself is generally only responsible for CRUD operations. It's used as an access point for data, rather than the object being responsible for more generalized behavior. In some instances, it can also handle saving and loading. Value List Handler. This pattern manages static or frequently used lists, such as drop-down options or enums. It serves as a catalog of predefined values that rarely change, but are accessed repeatedly, ensuring consistency and simplicity. Examples might include the cardinal directions or a list of all countries in the world. However, this pattern is unsuitable for dynamic or large datasets. The Snapshot Pattern. A way to capture the state of an object at a specific moment in time. Where the Memento pattern is often intended to preserve and later restore a prior state, the Snapshot pattern merely records state for later comparison or audit. Both patterns increase memory use and complexity as the size and interconnectedness of objects grow. Security patterns. These patterns center around limiting access and preventing undesired modification. Authorization patterns. Security mechanisms that determine what actions a client is allowed to perform on system resources, such as files, services, or application features. Actions can be as simple as mere knowledge that a resource exists, all the way up to total control of said resources. Authorization often follows authentication, verifying the client's identity first. A simple example is a dictionary mapping unique identifiers, such as usernames or passwords, to their access permissions. More robust systems may require multi-factor authentication or multiple access levels. However, overly complex protocols can lead to delays or bottlenecks, particularly when time-sensitive access is needed. The Secure Proxy Pattern. A mechanism by which the client remains one or more steps removed from the actual object or service being requested. A proxy object or proxy service acts as a middleman between the client and the target, such that the client never has direct access to the real thing, but can still get what they need. For example, a bank client cannot directly modify account details. Instead, they interact with a teller or online interface, which enforces the bank's policies and validates actions. Secure proxies can log actions, enforce access controls, or sanitize requests. However, proxies themselves can become vulnerable if they are compromised. Single Access Point. A design that consolidates all access to sensitive code or resources through a single, predefined entryway, eliminating backdoors. For example, a class with private fields may use public getters or setters to control access. Similarly, Singleton or core patterns can centralize interactions with critical data or behaviors. Additional safeguards like input validation or authentication can further restrict access. However, this pattern requires careful design to avoid bottlenecks or loss of access if a single entry point fails or becomes inaccessible, such as forgetting your password. Intercepting Validator. A pattern where filters intercept requests or responses to validate, modify, or block them. Filters, such as guard clauses or middleware, can check conditions, sanitize inputs, or apply security policies. These can be chained together to enforce rules, route requests, or handle exceptions without altering the underlying logic. For instance, an API might validate tokens, log activity, and sanitize data before processing. While flexible, overly complex chains can introduce latency or obscure the flow of control. The Secure Factory and Secure Builder patterns. An extension of creation patterns like Factory or Builder, where sensitive information must be protected during object creation. For instance, a secure factory might validate inputs, encrypt outputs, or restrict access based on user roles. This ensures that sensitive data like API keys, passwords, or configurations are handled discreetly. While this adds a layer of security, it can also increase complexity and require additional safeguards against factory misuse. Private Class Data Pattern. Sensitive data needs protection, even within your own codebase. This is especially important if working in teams or other scenarios in which making data public could lead to unwanted outcomes. The private class data pattern encapsulates this information in a helper class, keeping it away from the core logic. In other words, it hides the data in several nested layers, like a bank vault, and requires a very specific path in order to access it. For simple objects, or objects in which security is not an issue, this approach can be overkill. Concurrency patterns. These patterns deal with behaviors taking place at the same time in parallel, used most often in multi-threading. A thread represents a single sequence of instructions that can be executed independently by the CPU. In modern programming, threads allow a program to perform multiple operations concurrently, making use of multi-core processors for improved performance and responsiveness. Multi-threading refers to the ability of a CPU to execute multiple threads simultaneously, either by switching between them rapidly on a single core or by running them in parallel on multiple cores. This allows programs to perform multiple tasks at the same time, such as updating the user interface while processing data in the background. When multiple threads access shared resources, such as variables or data structures, there is a risk of conflicts, known as race conditions, if proper synchronization is not used. Thread safety ensures that the shared resource is accessed in a way that prevents data corruption or unexpected behavior. Concurrency refers to the ability to run multiple tasks in an overlapping period of time, but not necessarily simultaneously. This is usually achieved by switching between threads rapidly on a single core processor, known as time slicing. Thread pool. A thread represents a single sequence of instructions that can be executed independently by the CPU. Instead of creating a new thread for every task, you reuse a pool of threads, similar to object pooling. This is widely used in almost every application that handles multiple tasks, like processing web requests or handling game logic in parallel. Its simplicity and efficiency make it an essential starting point for learning about concurrency. The producer-consumer pattern. A way to introduce coordination between threads. One set of threads produces data, and another consumes it. A shared queue acts as the middleman, balancing the flow. This is perfect for scenarios like logging systems or data pipelines, where tasks are unevenly produced and processed. Guarded suspension. When multiple threads access shared resources, such as variables or data structures, there is a risk of conflict, known as a race condition, if proper synchronization is not used. Thread safety ensures that the shared resource is accessed in a way that prevents data corruption or unexpected behavior. Guarded suspension is the idea that threads only proceed when it's safe to do so. In programming, this reduces wasted computation by suspending threads until conditions are met, like waiting for data to arrive in a queue. Delaying behaviors until a particular point in the lifecycle is one means of achieving this. The barrier pattern. A way to introduce the concept of synchronization between multiple threads. Imagine a relay race where runners must wait at the next checkpoint for their team members. All threads pause until they've reached a specific point, then proceed together. This is common in parallel computing when different threads need to align their progress. The read-write lock pattern. A way to build on basic locking concepts. It allows multiple threads to read a resource simultaneously, but ensures only one can write to it at a time. This pattern is great for scenarios with lots of reading and occasional writing, like caching systems. The active object pattern. A means of introducing asynchronous task handling. Instead of doing work immediately, method calls are placed in a queue and executed one by one. This is useful in GUI applications or game engines and other real-time simulations to avoid blocking the main thread. The monitor object pattern. A means of simplifying thread synchronization by encapsulating it in a single object. The monitor ensures threads access shared resources in a controlled manner. It's a versatile pattern, but can create bottlenecks if overused. Double-checked locking. A means of refining thread-safe initialization, like checking if a door is already locked before retrieving the key. It's commonly used in Singleton implementations to ensure resources are initialized only once. In programming, this minimizes performance overhead by only locking threads when absolutely necessary. The lock split, or striped locking pattern. A way to optimize performance by dividing locks across smaller regions of data, like having multiple checkout lines at a store instead of one. It's ideal for large datasets where multiple threads can work independently, such as hash tables. However, it adds complexity in managing locks. The scheduler pattern. A way to assign tasks to threads based on priority or availability. This ensures tasks are completed efficiently while balancing resource usage. It's great for optimizing multi-threaded applications, but can be tricky to implement fairly. The balking pattern. A means of rejecting requests if an object isn't ready. Imagine trying to start a car that's already running. It won't do anything. This is useful for operations that should only happen under specific conditions, like initializing a connection only once. The future or promise pattern. Used to handle asynchronous operations, a future focuses on retrieving a value or an error when the operation completes, while a promise includes the ability to explicitly resolve or reject the result. This pattern helps manage complex asynchronous workflows and avoid callback hell. It represents a placeholder for a result that may not yet be available but will be resolved or rejected in the future. This pattern is particularly powerful when combined with async await, enabling clean, non-blocking code for asynchronous tasks like downloading assets, fetching APIs, or managing timers. Improper use can cause deadlocks. Asynchronous operations make stacks harder to trace and thus can make error detection more difficult. The work stealing pattern. A means of maximizing efficiency by redistributing tasks. If one thread has too much work, others can steal tasks from it. This pattern is ideal for dynamic systems with unpredictable workloads, like parallel algorithms. High traffic could result in all threads being overloaded simultaneously, leading to performance issues. The rate limiter pattern. A means of restricting how often tasks can be executed. This is useful for throttling API requests or controlling system load. You've probably received messages on your phone, internet, social media, or messaging system at some point telling you that you've been rate limited. Well, this is why. Because too much information is being sent at one time. It's a simple means of preventing system overload, modulating traffic, and preventing malicious behavior like spam. The leader-follower pattern. A way to rotate responsibility among several threads. This pattern balances workload and reduces contention. It's common in server systems where threads handle incoming connections. Testing patterns. These patterns are generally used in unit testing and other forms of verification or debugging. They often involve artificial data or artificial objects deliberately designed to confirm or break various systems and functions. The term SUT, or System Under Test, is often used to refer to the things we're trying to check. The test stub pattern. An empty shell of a real class with hard-coded return statements. Stubs provide canned answers to method calls and generally ignore anything that's outside the scope of the test. Stubs might also record information about the call for later analysis, though they generally don't validate the output or perform any sort of logic beyond returning hard-coded values. They're designed to provide predetermined responses that are easy to isolate and check while removing unnecessary dependencies. Hard-coded values can limit flexibility of testing. This pattern also won't catch dependency problems. The test spy pattern. A silent observer that reports on a process without interfering in said process. A given system might produce different results depending on its environment or context, thus making predictions about the outcome impossible. For instance, adding a mock object could change the results of our test compared to a real object if the system is highly sensitive to things like user input, object placement, or exact data matching. In that case, we can insert a test spy component to observe and report on what actually happens when the real object makes a method call. We can then compare the results to our expected value. The fake object pattern. A lightweight version of a real object used to verify some behavior. Where a test stub injects hard-coded inputs into a system, a fake object does not. A fake object can have the full implementation of a real class, but otherwise takes some shortcut that makes it unsuitable for production. For instance, an inventory with dummy items, or a character controller that uses placeholder models to test whether state transitions are working properly. If a fake does not accurately reflect real conditions, it could result in false positives. The mock object pattern. A way to implement behavior verification without necessarily duplicating test code. A mock object has the same interface that a system under test requires. We then configure it with values to give the SUT and method calls to expect from the SUT. Like fake objects, they are limited in some way and thus not useful in production. Unlike fake objects, they might not have full working implementation. Mocks can be used when the real object hasn't been created yet, when the real object is complex or slow to create, when the real object has non-deterministic behavior, or if the real object has states that are difficult to reproduce and must be artificially replicated for testing purposes. Mock objects can have information and methods used solely for testing, such as logging statements that confirm when a behavior has been triggered. This pattern tightly couples tests to their implementation, which can make them easy to break. Golden Master, or Characterization Test. A means of describing or capturing existing behavior in such a way that protects it from unintended changes. This is often a concern with legacy code and backwards compatibility, wherein changes to a codebase must not break other systems that depend on its present form. This becomes less relevant as older code becomes deprecated and is no longer supported or maintained. Characterization can also be used when exact functionality is unclear, or to avoid fixing the problem without first understanding how or why it works, thereby stifling the ability to recreate the problem in the future. If errors exist within the master, they will continue to exist afterward. This pattern can be hard to maintain if changes occur frequently. Data-driven testing. A methodology that decouples test logic from test data. Test data is often stored separately, such as in an external file, spreadsheet, or database. This allows the same tests to be run with different datasets, enabling broader coverage and flexibility in testing. If a dataset is complex, or if there are too many being tested simultaneously, this can make debugging more difficult. Property-based testing. A means of exploring the behavior of a system by asserting general properties or rules instead of specific examples. Rather than testing individual inputs and outputs, it generates a wide range of input data to validate whether the system consistently behaves as expected. For instance, when testing a calculator, instead of writing separate tests for 2 plus 2 and 3 plus 5, you assert the property that addition is commutative, so x plus y must equal y plus x. This approach is particularly useful for edge cases and uncovering hidden assumptions in complex systems. Properties must be carefully defined to avoid false positives. Behavior-driven development. Sometimes referred to as the give-when-then pattern, a convention in which tests are named based on what conditions exist, what behavior is being tested, and what the expected result should be. Often, these are written as full sentences using natural language. For instance, given some condition, when event happens, then ensure some outcome. This approach is meant to help improve communication in software development and clarify what tests are or should be. This practice does not necessarily dictate how a test should be written in syntax and is more akin to pseudocode. The Arrange-Act-Assert pattern, a convention that structures tests along a particular order of operations. First, we arrange inputs and targets, those things that the test needs in order to run. Next, we act on the behavior, such as calling a method or interacting with a web page. Finally, we assert expected outcomes and evaluate the response. The goal of this pattern is clarity and ensuring that tests have a logical flow, making them easier to understand and debug. This pattern is simple, but over-reliance can lead to verbose tests. It's also not useful for more complex tests. All right. Just a quick pause before we continue to check in and see how you're doing. You're about 2/3 of the way through the entire series. Great job. I hope you're learning something from it. If you are, just a reminder to please leave a like and share this video with others as it helps out the channel. If you're finding this to be a bit overwhelming, that's okay. Feel free to take a break and come back to it as many times as you need to. If this is your first time hearing about these patterns, remember that it's not necessary for you to learn all of them in one sitting. In fact, giving yourself time to sit and reflect and practice what you've learned can help it sink in a lot better. Also, feel free to ask questions or leave comments down below. And with that, we move on to UI patterns. These patterns center around the user interface, that portion of the program with which the user directly interacts. The presentation model pattern. a way to separate the logic of a user interface from its visual representation, creating an abstraction that can be tested independently of the UI. This allows the same logic to be reused across different views, useful for different platforms or even between different projects where only the visuals change. The View Helper pattern, a way to introduce helper classes or components to encapsulate common presentation logic, keeping the view focused solely on rendering and user interactions. For instance, any of the various UI components inside a game engine or web builder. This practice can tightly couple view logic to the helper, which may or may not be desirable. The Page Controller pattern, a way to manage the logic of a single page or screen in an application. It handles input, manages navigation, and coordinates between objects and their representations. Used most often in web applications and game design. Scaling can become challenging as the number of pages grows, leading to duplicated logic across multiple controllers. The Application Controller pattern, a way of managing application-wide logic, such as navigation, user authentication, or error handling, decoupling these concerns from individual views or pages. It's used in applications where shared behavior needs to be managed globally or where modularization of page controllers is necessary. This pattern can become a bottleneck or monolithic if too much responsibility is placed on the central controller. The Front Controller pattern. A single controller handles all requests, delegating them to appropriate handlers or controllers. This centralizes request handling and simplifies routing, akin to an information help desk. It's used in applications that require a unified entry point for all requests, such as applications with consistent pre-processing, like security checks or logins. This pattern is also highly vulnerable and can become a single point of failure if not careful. Complex routing logic can also make maintenance more difficult. Command Query Separation, or CQS. A principle that separates methods into commands that change state and queries that return data, ensuring each method does one or the other but not both. Used in applications where clarity and separation of concerns in UI behavior are important. It's particularly helpful in ensuring predictable state changes and enhancing testability. However, it can also lead to more verbose code and boilerplate, especially for simpler applications. Presentation Abstraction Controller, or PAC. A means of dividing an application into three distinct parts. Presentation groups input and visuals, abstraction groups logic and data, and control represents managers that communicate between the two. This pattern is used in complex, distributed systems where modularity and independent components are necessary, such as multi-tiered client-server applications. In some instances, it may be desirable to further split presentation and abstraction into their constituent parts. However, an overly complex hierarchy can make debugging more difficult. Enterprise Integration Patterns. These patterns generally deal with messaging and communication between multiple systems. The Service Layer pattern, a way to organize system logic in an application. It acts as an intermediary between the client and the domain model. The client in this case is either UI or an external service, while the domain contains system logic and data access. The service layer encapsulates the system operations, providing a simplified API for clients. The Data Transfer Object pattern, or DTO. Used to transfer data between layers of an application or between systems. DTOs are lightweight objects that don't typically contain any logic, but only hold data for transfer. DTOs can lead to redundancy if you have too many types that essentially contain the same information. Managing them can become cumbersome, especially in systems with numerous endpoints or layers. The Message Broker pattern. A middleware component that handles exchanges and routing between applications or systems, allowing them to communicate in an asynchronous manner without being directly connected to each other. While it decouples systems, it can become a single point of failure. Heavy loads can also cause latency issues. The Message Queue pattern. A way to hold messages sent between services or applications. It ensures that messages are processed asynchronously and guarantees that messages are not lost even in case of service failure. It's helpful in situations where services need to process tasks in the background, or in cases where operations might be time-consuming or resource-intensive. Message queues can add complexity by introducing an additional layer for message processing. Also, if the queue becomes too large, or services fail to process messages in time, it can result in message backlog, leading to performance degradation. Enterprise Service Bus, or ESB. A central hub for routing, transforming, and handling messages between components. Start by defining an interface with a method for handling messages. Child classes will provide specific implementations. The ESB will keep a list of all services that need to be notified and a way for objects to register calls. When an object calls the ESB, asking it to send a message, the ESB will loop over all registered services and notify them. Use this pattern when you have a large, complex system that involves numerous applications or services that need to communicate in an integrated manner. ESBs can become overly complex and require significant overhead for setup and maintenance. They can also become performance bottlenecks and single points of failure in large distributed systems. The Aggregator pattern. Used to gather messages or data from multiple sources and combine them into a single message or data structure. This is often used when you need to collect information from different services or systems and consolidate it into a unified response. The aggregator can become a performance bottleneck if the aggregation process is too complex or if it collects large amounts of data. It can also introduce tight coupling between the components that need to aggregate data. The splitter pattern. The reverse of the aggregator pattern. It splits a single message into multiple smaller messages, which can then be processed independently. After processing, the results can be reassembled if needed. Use the splitter when you need to break down a large request into smaller, manageable parts for parallel processing. Splitters introduce complexity in how data is partitioned and later reassembled. If not handled properly, splitting and merging data can lead to inconsistency and hard-to-debug issues. The content filter pattern. Used to filter out unwanted content from messages or data as they pass through a system. This can include sanitizing data, removing irrelevant information, or preventing issues such as security vulnerabilities or data corruption. Poorly designed filters may allow malicious data to slip through, or, conversely, overly restrictive filters can block legitimate data. Filters can add overhead in terms of processing time and complexity, especially if multiple layers of filtering are involved. The message translator pattern. Used to convert messages from one format to another. This is typically required when different systems or services use different data formats. Functions like from.json or to.png would be examples of this pattern. Care must be taken to ensure accurate translation. Cloud patterns and distributed system patterns. These patterns help applications work across multiple systems, sometimes in different locations. They address challenges like network reliability, distributed data consistency, fault tolerance, and managing large-scale resources. The cloud refers to a network of servers and data centers that allow users and organizations to store and access data and applications on demand over the internet, rather than relying on local storage or hardware. The circuit breaker pattern. A way to prevent an application from repeatedly trying to execute a failing operation by detecting failures and halting further attempts for a period of time. This is used to avoid overwhelming the system with repeated requests that will likely fail, allowing the system to recover. This pattern is used when your system relies on external services, APIs, or databases, and you want to avoid repeated failures. A balance must be struck between failure threshold and cooldown periods to avoid affecting legitimate traffic. If the circuit breaker is triggered too frequently, this can lead to delays, whereas aggressive failure detection may lead to unnecessary downtime. The bulkhead pattern. A way to isolate failures in different parts of a system to prevent cascading failures. By splitting the system into independent isolated parts, known as bulkheads, you ensure that the failure of one part does not bring down the entire system. This pattern is used when your system contains different subsystems that can fail independently, but its use is not without cost. More overhead is generally needed for managing resource allocation and usage. Misjudging the timing of shutoffs can lead to underutilization or overloading of resources, and care must be taken when designing partitions to reduce overall impact. Leader election. A technique that selects a single node or process as the leader, responsible for coordinating tasks across the system. This is essential in distributed systems, where one node must take charge, and be the final arbiter in order to ensure consistency and avoid conflicts. Complexity scales with the size and number of systems being governed. The process of electing a leader can itself be resource-intensive and require frequent communication between nodes. The leader can also become a single point of failure, requiring re-election, which can further impact availability of resources. The sharding pattern, a means of breaking data up into fragments and scattering it across multiple databases or nodes to distribute load and improve scalability. Each partition, or shard, holds a subset of the data, allowing the system to scale horizontally by adding more shards. This pattern is useful when you need to handle large volumes of data, or when scaling vertically, i.e., increasing the capacity of a single machine, becomes inefficient. It's also useful for systems with high throughput requirements. The process introduces complexity and disruption across multiple shards, and load balancing can become difficult as the system grows. Command Query Responsibility Segregation, or CQRS. A means of separating the read and write operation of a system, queries being read and commands being write. The command side handles data modification, while the query side handles data retrieval, improving performance and scalability. A simple property might share a getter and setter, but splitting these into separate functions might be better if one or both operations have different or complex logic. This pattern is also useful if one half requires more optimization than the other. If not careful, it could introduce latency issues or lead to data duplication. The saga pattern, a long-running process that coordinates multiple microservices or steps. Each step in a saga is a transaction that can be either committed or rolled back. If a step fails, compensating actions are triggered to undo the previous steps. For instance, planning a vacation might involve booking a flight, checking into a hotel, and renting a car, each of which is a separate service. If we've booked our flight, but a hotel is not available, we can then call to cancel our flight as the trip cannot be completed. These undo actions, combined with the number of steps and the number of potential fail points to manage, can all make sagas inherently complex. Steps that call external services can also introduce latency. Serverless patterns. These patterns focus on leveraging serverless computing to build applications that scale automatically with events, without managing servers or infrastructure directly. The term serverless does not mean there are no servers. Rather, it means that the cloud provider abstracts away the management of servers. This approach is used when event-driven scalability and minimal infrastructure management are priorities. However, they come with trade-offs such as cold starts, vendor lock-in, and resource limitations. Serverless architecture can be tightly coupled to the cloud provider's ecosystem, making it difficult to migrate without significant refactoring. Optimization patterns. These patterns focus on improving the efficiency of a system, particularly in areas like performance, resource utilization, and response times. Caching. The process of storing frequently accessed data in a faster storage layer, such as memory, to improve performance and reduce the load on the underlying data source. You should cache data and references when the cost of fetching them is high, when they're read frequently but written infrequently, or as a means of improving responsiveness in performance-critical areas. Caches are not free. They do require memory, which can create a bottleneck in resource-constrained environments. An unused cache is simply wasteful. A cache can also become stale if not removed or updated. The caching process itself can also add complexity. Lazy load. The act of delaying retrieval of resources until they're needed. While lazy initialization is about delaying the creation of an object, lazy load is more about fetching or loading data, often from an external source, such as a database, a file, or a network request. This process can introduce latency at the point of first access. In distributed systems, lazy loading may delay error detection, as issues won't surface until access occurs. Read-through cache. A mechanism that ensures the application interacts only with the cache. If the requested data is not in the cache, it automatically fetches it from the data source, caches it, and returns it. Use this pattern for read-heavy systems or when data retrieval and caching should be handled transparently. This pattern necessarily creates a dependency between the cache and its data source. If a cache is missed, it could add latency. Write behind cache. A mechanism that defers writes to the underlying data source, first writing to the cache and asynchronously updating the data source afterward. Uses to improve write performance for applications with high write throughput or when immediate consistency with the data source is not required. This pattern risks data loss if a crash occurs before updates are written to the data source, and thus may not be suitable for systems requiring real-time data accuracy. Micro-optimization patterns. These patterns deal with highly granular performance improvements, often addressing very specific aspects of a system's behavior. While these patterns can lead to performance gains, excessive micro-optimization can also lead to overly complex or hard-to-maintain code. These patterns typically focus on individual lines of code or specific operations to improve speed or reduce resource consumption at a very fine level. For instance, if you've ever multiplied by 0.5 instead of dividing by 2 because division is a more expensive process than multiplication. Object recycling. A way of reusing existing objects instead of creating new ones, thereby avoiding the cost of object creation and garbage collection. This pattern is widely used to maintain performance in systems where objects are frequently created and destroyed. Where object pooling focuses on maintaining a collection of multiple objects, recycling instead focuses on reusing a single object efficiently, even outside of a pool. The object is reset and reused by the same or another process. Recycling does not scale as well as object pooling for a large number of objects, and can lead to tight coupling if its reset logic is tied to the object's class. Data-oriented design. A means of organizing data in memory to maximize cache efficiency and reduce latency. Instead of thinking in terms of objects, it organizes and processes data in large, contiguous chunks that CPUs can handle more efficiently. This approach is usually favored in so-called functional programming languages that deal mainly in verbs rather than nouns. It's highly compatible with the ECS pattern and is used in application where performance is critical, such as games and simulations with large numbers of entities, such as real-time fluids. Unity Engine has an entire workflow built around this pattern, with its burst compiler and data-oriented technology stack, or DOTS. This program can be extremely challenging for those who are used to working in object-oriented programming. Single Instruction Multiple Data, or SIMD. A process that allows a single CPU instruction to operate on multiple pieces of data simultaneously. This process works best on data structures like arrays and vectors, or where the same operation is applied to all elements. Imagine painting a large fence. We can use one brush to paint one plank at a time, or attach 4 brushes in parallel to one handle and paint 4 times as much in the same stroke. This works because all the planks will ultimately be painted the same way in the end. We're just speeding up the process. You can use this pattern for operations that are computationally expensive and need to be run in parallel, like physics simulations, AI, graphics such as compute shaders, or scenarios with heavy mathematical calculations that can benefit from vectorization, such as quaternion transformations. This process breaks down, however, if we have to rely on the CPU to make constant changes to our instructions, such that all elements are no longer treated the same way. Another major limitation is hardware support, as not all processors have equal SIMD capabilities, meaning your GPU. Setup is also more involved than most other patterns. Emergent patterns. The following patterns don't really fall into other categories, or are relatively new. The game loop pattern. A process that updates the application state and renders visuals frame by frame. This pattern is foundational for any real-time simulation. Most game engines implement this by default. For instance, Unity Engine has an explicit update method as part of its lifecycle within the mono-behavior system. Poor structure of logic within the update loop can lead to errors and spaghetti code. The Dependency Graph pattern. A way of representing dependencies between objects or tasks, often used for resolving execution order or managing dependencies in complex systems like UI rendering or task pipelines. Nodes are often best expressed visually for more intuitive comprehension. Complexity increases with the number of dependencies, and cyclical dependencies can cause infinite loops. Idempotent Receiver. A means of ensuring that processing a message multiple times has the same result as processing it once, used in distributive systems where duplicate messages may occur. We might use a global variable to track whether a certain process has been run. At the start of a method, That flag is used in a guard clause that returns early. If the process hasn't been run before, we run as normal and set the flag to true at the end. For instance, if an error occurs every frame, you can limit the number of logs or pop-ups to only notify you the first time and then dismiss it. This pattern requires additional storage to track processed messages, such as in a bool or hash set. The sidecar pattern. Auxiliary functionality is moved into a sidecar process that runs alongside the main application. This is common in microservices architecture to handle tasks like logging, caching, authentication, or monitoring without complicating the primary service. Also used in distributive systems to keep concerns like security or telemetry separate from the main application. Complexity increases with the number of processes, and latency can occur between the sidecar and main service. The ambassador pattern. An intermediary that augments or manages remote communication on behalf of a service. Where the mediator handles local objects and the broker handles distributed systems, the ambassador generally deals with external services, particularly those that involve retries, logging, and monitoring, or when using unreliable or slow networks. Risk of latency is increased as it inherently deals with remote systems. The event loop pattern. A programming pattern that continuously waits for and processes events. It's foundational for asynchronous systems like GUIs or server message handling. An input system is a good example of this pattern, as it constantly checks for inputs and then fires off events when it detects one. Other systems can then listen for those events while carrying on their normal business. Metadata mapping. A pattern for mapping metadata to behaviors or objects dynamically at runtime. Metadata refers to data about data, such as its properties, structure, or context. Used for systems with a strong separation between data and behavior, like configuring objects using external JSON or YAML files. Errors in metadata can lead to runtime errors. This pattern can also lead to indirect or hard-to-follow paths. The value object pattern. An immutable object representing a value, often used to encapsulate complex values, such as currencies or measurements. Useful when you need objects that compare by value rather than by reference. Structs are a form of value object, while classes are a form of reference object. The immutable nature of value objects means they require more memory allocation. In order to modify a value object, you either need to create a new one or modify the underlying data they contain. Value objects are also useful as records in functional programming. The optional pattern. A container for encapsulating optional values. It's a type-safe way to handle cases where a value might not exist. Used to avoid null references and to make the absence of values explicit. This pattern works well with generics, though additional wrapping and unwrapping create more overhead compared to a simple null check. Interpreter context. A process for designing a language interpreter. It creates classes to help define grammar rules and evaluates them. Used when implementing a custom scripting language, such as combining C# and Lua, or when evaluating mathematical expressions, such as building a calculus library. Risk of complexity is high. The event replay pattern. A way to process events from a log to reconstruct state, used primarily in event-sourced systems where historical event data needs to be replayed. Cheat detection and crash logs are an example of this pattern. Event logs can grow large and potentially impact performance. Domain-specific patterns. These patterns focus on solutions tailored to particular domains or problem areas. They often arise from common practices or techniques that have proven effective in specific industries or use cases. They aim to provide reusable solutions for recurring problems in those domains. Spatial partitioning. A design pattern that organizes space into regions to optimize operations like collision detection, rendering, or pathfinding. Common techniques include quadtrees, octrees, and spatial hashing. Often used for games or simulations requiring efficient management of entities in large 2D or 3D spaces, such as managing AI units, bullets, or environmental effects. Choosing an incorrect cell size can result in inefficient performance. This pattern requires careful updates when objects move from one cell to another. The data pipeline pattern. A way to send data through a sequence of transformations or processing stages. Often used for streaming data, AI training pipelines, or procedural content generation. used when your project involves processing large amounts of data in stages, such as image processing, animation, or procedural world generation. Complex pipelines can be hard to debug, and overhead is involved in chaining functions. The task queue pattern, a way to schedule tasks to be executed asynchronously, often in the background. Commonly used in server systems or asynchronous gameplay logic. Coroutines and tweens fall under this pattern, where actions are performed over multiple frames. Other examples include pathfinding, background loading, and task-based AI systems. Tasks generally require manual scheduling and prioritizing, as well as management of their life cycles. If there are any design patterns you think we missed, let us know in the comments below. If you found this video helpful, please make sure to like, share, and subscribe so you stay up to date when we release new content. If you'd like to learn more about programming and game design, click on the link appearing on your screen now, or see the description below for ways you can help support this channel. Thanks, and take care.